The research paper presents the development of a groundbreaking 100-channel Picosec Micromegas detector, boasting an unprecedented sub-20 picosecond time resolution. This innovative device is designed to significantly enhance precision in particle detection and timing for various applications in high-energy physics, nuclear physics, and medical imaging. The authors, representing several international institutions, have developed this novel device as part of the European Organization for Nuclear Research (CERN) project. The detector's architecture is based on the Micromegas principle, which uses a micromesh structure to amplify the signal from charged particles interacting with the detector material. Detailed descriptions of the detector's design, construction, and operational principles are provided in the paper. It also outlines the experimental setup used to test the detector, including the data acquisition system and the calibration procedures. The results show that the detector achieves a time resolution of 15 picoseconds for minimum ionizing particles, making it one of the fastest detectors in its class. The paper highlights the potential applications of this technology in various fields such as particle physics, nuclear physics, and medical imaging. For instance, in high-energy physics, such a detector could be used to identify particles and measure their time of flight with high precision, allowing for more accurate event reconstruction. In nuclear physics, it could help in timing coincidence measurements between different detectors. In medical imaging, the detector could be applied in positron emission tomography (PET) scanners to improve image quality and reduce radiation exposure. The authors also discuss the limitations and challenges encountered during the development process, including issues related to the manufacturing of the micromesh and the optimization of the detector's operational parameters. They propose future work directions, such as improving the detector's stability and exploring new materials for the micromesh. In conclusion, the paper presents a groundbreaking achievement in the field of particle detection and timing. The proposed detector offers unprecedented time resolution, paving the way for significant advancements in various scientific disciplines. The research team's innovative approach and meticulous work have led to a device that could revolutionize the way we understand and interact with subatomic particles. The Picosec Micromegas detector, a novel Cherenkov radiator-based gaseous detector, has demonstrated promising results in achieving time resolutions below 25 picoseconds. This detector utilizes a semi-transparent photocathode and a Micromegas amplification structure, featuring a modular design capable of large area coverage for high-energy physics experiments. The first multipad prototype, consisting of 19 channels with an active area of approximately 10 square centimeters, showed degraded timing resolution due to non-uniformity in the preamplification gap. To address this, a new 100 square centimeters detector module was developed, featuring 100 channels and a rigid hybrid ceramic, FR4 Micromegas board for enhanced drift gap uniformity. Initial measurements using 80 GeV muons revealed improvements in timing response across measured pads, achieving a time resolution below 25 picoseconds. Recent advancements include the introduction of a thinner drift gap detector module and newly developed RF pulse amplifiers, leading to further enhancements in time resolution, reaching levels as low as 17 picoseconds. This paper presents the development of the detector from structural simulations, design, and beam test commissioning, focusing on the timing performance of the thinner drift gap detector module when combined with new electronics. An automated timing scan method was employed to assess the detector's performance accurately. The paper also explores various micropattern gaseous detectors, such as MSGC, GEM, THGEM, RETHGEM, MHSP, MICROPIC, MICROMEGAS, INGRID, and others, highlighting their potential applications in timing detectors and Cherenkov detectors, and comparing their performance characteristics. The development of precise timing detectors with large area coverage and high radiation fluence capabilities is crucial for future physics experiments. The Picosec Micromegas detector, featuring AM amplification structure coupled to a Cherenkov radiator with a CSI semi-transparent photocathode, has demonstrated promising time resolutions of tens of picoseconds. This two-stage amplification structure operates with a Na. C2H6. CF4, 80 hours 10 minutes and 10 seconds, working gas mixture. Initial single-channel prototype measurements with minimum ionizing particles, MIPS, achieved time resolutions below 25 picoseconds. However, subsequent multi-channel detector development revealed issues with drift field non-uniformity, which were mitigated through flatness corrections based on particle hit position, resulting in a uniform time response and a time resolution of 25 picoseconds in the best case. To address these limitations, a new 100-channel prototype was designed with improved flatness and uniformity of the drift gap. Structural mechanics simulations of the mesh tension interface and coupling to the detector casing informed the selection of a substrate ensuring planarity better than 10 micrometers over a 100 square centimeters active area. Finite element analysis suggested the use of a more rigid and thicker printed circuit board, PCB, comprising a 4 by 1 mm thick ceramic core with 0.3 mm thick FR4 outer layers. This design improvement aimed to address initial deformations observed in the MPCB, likely caused by production processes and mesh stretching. The mechanical design enhancements enabled the development of an even larger multi-pad Picosec detector. The results of the mechanical aspects and timing performance of the 100-channel prototype are presented in Figure 1, which shows the simulated mesh tension interface and coupling to the detector casing. The mechanical design of the detector plays a crucial role in ensuring optimal performance of the Cherenkov radiator and the multi-pad board. To mitigate the effects of mesh tension, simulations were conducted to model the influence of mesh tension on 4 mm thick ceramic, applying a shear force of 15 N per centimeter to the coverlay faces directed inward the active area. The results, presented in Figure 1, demonstrate the impact of mesh tension on the ceramic's rigidity. The detector's readout structure consists of a 10 by 10 matrix of square pads, each measuring 9.82 mm by 9.82 mm and spaced 200 micrometers apart. The pad layout is shown in Figure 2, where the blue squares represent the pads used for evaluating the timing performance over the detector area. Thin FR4 layers were utilized in the detector's construction to ensure precise flattening and polishing. The outer board, OB, and flange were designed to mechanically detach the active detector components from the housing, preventing bending of the board or flange when pressed with screws. The signal from each pad is routed to the SMB connectors on the top of the OB via spring-loaded pins, which provide both electrical connection and compressive force to press the radiator firmly and evenly into the positioning groove in the chamber. The detector's time response was measured at the CERN SPSH4 secondary beamline using a 100-channel detector under test, DUT, and 80 JV muons. The setup consisted of a triple gem detector telescope for particle hit position information and MCP-PMTs as a timing reference or trigger. In a standard readout chain configuration, an induced signal from the Hamamatsu MCP-PMT-R3809U50 was used as a reference. The development of a large area Picosec detector is presented, focusing on the experimental setup and initial results obtained from the prototype detector. The setup consists of a high bandwidth CIVIDECC2 amplifier and a Lecroy WR8104 oscilloscope, digitizing signals at a sampling rate of 10 Gs. Recorded waveforms are analyzed using established methods. Initial measurements employed a prototype detector with a 220 micrometers drift gap thickness and a CSI photocathode on a thin crossing layer. Two MCP detectors were aligned in the XY plane, with the device under test, DUT, positioned behind them. A trigger detector and timing reference MCP were used to collect data from particles crossing an entire pad area. Measurements demonstrate a time resolution below 25 ps for each pad in its central 5 mm by 5 mm area, replicating the timing properties of the single-channel prototype. To further improve timing, the dependence of signal arrival time, SAT, on electron peak charge is investigated. Uniform drift fields across the pad surface would result in similar SAT and time resolution dependencies on peak charge for all pads, suggesting a single global time walk correction function could be applied to all pads, simplifying calibration. Timing measurements from 7 pads in the same row assessed performance over a larger area. Analysis reveals that all pads closely follow the timewalk correction function, indicating consistent global behavior. This is crucial for many channel detectors, as shown in Figure 3. The results highlight the potential of the large area Picosec detector for achieving high precision in particle time of arrival measurements. Characterizing the timing performance of large area detectors relies on a reference detector with superior timing characteristics and spatial uniformity. However, large area microchannel plates, MCPs, are costly and require precise timing calibration to ensure unbiased measurements of the detector under test, DUT. Previous studies have shown that the timing performance of an MCP reference detector deteriorates rapidly outside its effective photocathode diameter, 11 mm. To mitigate this bias, a modified measurement method was developed. Analysis of minimum ionizing particle, MIP, interactions with the reference MCP revealed a double peak amplitude spectrum, correlated with hit positions obtained using trackers. Events in the lower signal amplitude peak originated from the outer region of the MCP, while those in the larger amplitude peak corresponded to central hits. By employing the central part of the MCP as a trigger and time reference with a high threshold, events from the outer region are rejected. The MCP was mounted on a movable stage, and an automated scanning method was used to cover the large DUT area, ensuring even data collection. The MCP was moved in a 2.5 mm by 2.5 mm grid every 1,000 events, resulting in a dense grid with 75% overlap to average out MCP imperfections. This approach reduces the load on the tracking system and oscilloscope recording, although it is time-consuming due to the geometric scan. It can be applied to measurements on a single pad, signal sharing, or entire detector scan studies. In a separate experiment, beam test measurements were conducted using custom electronics and a 180 micrometers drift gap thickness. Earlier measurements and simulations indicated that reducing the drift gap improves the time resolution of the Picosec Micromegas, IM. The results of these measurements are presented in the following sections. The development of a new 100-channel Picosec detector, with an area of 100 square centimeters, aimed to achieve a flat and uniform drift gap. This goal was pursued to ensure uniform timing over a large area. A prototype based on an embedded ceramic IM board confirmed the uniformity and preserved the time resolution of the single-channel detector. To investigate the uniformity of the drift field, the dependence of the single-ended timing, SAT, and time resolution on the E-peak charge was examined. A similar behavior to the prototype with the standard drift gap detector is found, as shown in Figure 5. This figure presents scan measurements of 6 pads, displaying SAT and time resolution for different E-peak charge bins, with a similar behavior measured for all pads. The RMS values of SAT distributions for tracks passing through the 4 mm by 4 mm pad central area during the scans are summarized in Tables 1 and 2. SAT distributions of all measured pads show RMS values of 17.1 picoseconds on average. Measurements were performed during 2 RD51 beam test campaigns in July and October 2022. In July, 2 sets of measurements were taken over a 4-pad area, while in October, a 6-pad measurement was performed. The motivation was to study the single-pad time response and signal sharing over multiple pads. The Picosec Micromegas detector development has reached a significant milestone, achieving uniformity with a shorter drift gap. Recent measurements demonstrate an average timing resolution of 17 picoseconds across all pads, a notable improvement. Ongoing efforts are focused on enhancing stability and robustness, as well as developing a full readout chain with a multi-channel SAM-PIC digitizer. This advancement is crucial for optimizing the detector's performance and paving the way for future applications. The development of the Picosec Micromegas detector is supported by various institutions, including the European Organization for Nuclear Research, CERN, the French Alternative Energies and Atomic Energy Commission, and the National Natural Science Foundation of China, among others. These collaborations have been instrumental in driving the project forward. The achievement of a uniform detector with a shorter drift gap is a significant breakthrough, enabling the attainment of a higher timing resolution. The use of a multi-channel SAM-PIC digitizer will further enhance the detector's capabilities, allowing for more efficient data acquisition and analysis. Future work will focus on refining the detector's stability and robustness, ensuring its reliability in various experimental conditions. The development of the Picosec Micromegas detector has far-reaching implications for particle physics and beyond, and continued support from collaborating institutions will be essential in realizing its full potential.